differentiating using the power rule. This is basically saying that if I've got something that looks like this, I can differentiate it by bringing the power down the front and multiplying by the coefficient. That's what this AN is doing, and then reducing the power by 1. We've used this a lot, and generally the types of functions that we've been dealing with have been things that look like this, with some kind of number at the front. Sometimes this has been positive or negative or a fraction, and some kind of whole number power. But this rule doesn't just hold when we've got nice whole numbers as the power here. We can actually deal with it. We can actually use this to differentiate anything that we can get to look like this, to be in this form, where we've got some coefficient times x to any power. N doesn't have to be a whole number. And this is going to be helpful to differentiate certain functions. And to do that, we're going to need to review our index laws from first term. There's two index laws in particular that we're going to find useful for our work on differentiation. First one is this one here. 1 on a to the n equals a to the power of negative n. Now, it looks scary when it's written in algebra, but all this is saying is that if I have something that looks like this, so some kind of 1 over x to any power, okay, 3, I can change the way that it looks to get it out of this fraction situation, and instead just write it as a regular x, but have the power as to the power of negative 3. So this power of negative 3, x to the power of negative 3, is the same as 1 divided by x. Similarly, if I took some, let's go negative 1 on 4x to the 5. Okay. If I wanted to deal with something like this, I can just treat this negative 1 on 4 as being like a coefficient. So these numbers here, they look scary, but they're not so bad. Just treat that whole blob there as some big coefficient. So in this case, it's negative 1/4. And this part here, to get it off the bottom of a fraction, I can just bring it to the side and make it a negative index there. So this expression, negative 1 on 4 x to the 5, is equal to, or it's the same as, negative 1/4 as a coefficient of x to the negative 5. Okay, so just that negative sign there brings terms out of the denominator and brings them into the numerator. Of an index law that's going to be useful when we're differentiating is this one here. Okay, this is the index law that allows us to change roots, so square roots, cube roots, and that sort of thing, into fractional indices. Fractional indices we're going to be able to apply the power rule to. These ones we can't really apply the power rule to. So let's look at a couple of examples of ways we could use this rule. If I gave you this, okay, the square root of x, this rule says, okay, that we can rewrite this as x to the power of 1 on whatever number is out the front of the square root. Now, when you don't have a number there, we're assuming it's a square root, so it's a 1 on 2. Okay, so the square root of x can be rewritten as x to the power of 1/2. Similarly, if I had the cube root of x, I could write that as x to the power of 1/3. Let's look at a few examples of how we use these power rules to differentiate various functions. So let's look at the first one, y equals 1 on x cubed. We've already discussed how this can be written using our index laws as x to the minus 3. Now, once I've got it into this form, we can actually just straight away apply the power rule to this result. So the power rule says I take the power and I bring it down the front. So in this case, it's going to be a minus 3x up front. And then I've got to subtract 1 from the power. So currently it's a minus 3. I've got to take 1 away from it. And that gives me x to the power of minus 4. So we actually find that this is the derivative of the function we started with. For comparison, we should probably leave it in the same form that it originally started in. So in this case, we're going to write it as minus 3, and x to the minus 4, we can write that as 1 on x to the power of 4. So we can write it into this form. And this is the derivative of the function that we started with. Similar example, the next function we looked at was a negative 1 on 4x to the 5. Again, we said before that this can be written as a negative 1/4 x to the power of minus 5, and we're able to differentiate this again by bringing the power down the front. So it's minus 1/4 times negative 5, x to the power of minus 5 minus 1 is minus 6. I've forgotten to put here that this is f dash of x now. Okay. That's an important difference when you go from the original function to its derivative. You need to use a derivative sign on the left hand side to kind of say that this is now a new thing we're dealing with. Anyway, I should tidy this up. Negative 1/4 times negative 5, I've got two negatives multiplied together as a positive. 1/4 times 5 is 5. Well, 5 on 4, x to the minus 6, and if you want to tidy up, let's have another go at that. 5 on 4x to the power of 6 is the derivative of this function. Example, this time one with a square root in it. So we're going to differentiate f of x equal to the square root of x cubed. Now, we're going to need to use our index laws on this one. This one's a little bit trickier because it's got sort of stuff going on the inside here, which can be a bit difficult. But the way we're going to deal with this, we're going to treat this whole center as just one blob, just sitting there as x cubed. And we know that a square root can be written as a power of 1/2. So if we write this like this, we can then use another index law to say that this thing here can find out, so I'll start that again, this thing here, when I've got an x cubed, all raised to the power of 1/2, I can deal with this double power thing going on here by just multiplying the powers together. So x cubed all to the power of 1/2 is the same as x to the power of 3 times 1/2. I'm going to leave this as an improper fraction because it's usually the way that we like to write things in maths. So this is that function in index form rather than with square roots in it. And from here, we're able to differentiate. So just as before, finding the first derivative, I can bring that power down the front, and I've got to subtract 1 from this. Now 3 on 2 is the same as 1/2. 1/2 take away 1 is just 1/2. And so in fact I'm left with this thing here, 3 on 2 times x to the 1/2. Again, if I want to tidy up, which I should probably do, 3 on 2 root x, and probably even write it like this, 3 root x on 2. Well, pen's not working. There we go. So this is the derivative of this function.